Hi, my name is Fahad Sarfaraz, and today I'm excited to present my joint work on the importance of integrating multiple modalities for lifelong learning. Our focus is on enhancing deep neural networks' ability to perform lifelong learning by moving beyond unimodal learning and leveraging multiple modalities. Lifelong learning requires AI agents to continuously adapt to new data while retaining and consolidating previously learned knowledge. This is crucial for the deployment of deep neural networks in many real world applications. However, one of the main challenges we face is catastrophic forgetting, whereby models drastically forget previously acquired knowledge when learning new tasks. Overcoming this issue is essential for enabling effective continual learning in dynamic and evolving environments. To this end, we look at the human brain, which excels at continual learning. The brain's ability to adapt to ever-changing environment can be partly attributed to processing and integrating information from multiple sensory modalities. Various neuroscience studies have shown that integrating sensory modalities enhances perception and cognition compared to processing them independently. In particular, integrating audio and visual information leads to a more accurate representation of the environment, improving both perceptual learning and memory. Therefore, a multimodal approach significantly enhances the brain's ability to acquire and consolidate new knowledge. Inspired by the human brain's approach, we hypothesize that integrating multimodal learning into deep neural networks can similarly enhance their lifelong learning capabilities. By combining information from different modalities, these models can develop a more comprehensive and robust understanding of their environment. This allows the model to create a more accurate representation that is less sensitive to modality specific regularities. While multimodal learning has shown promise in certain computer vision tasks, its efficacy in continual learning and optimal integration of modalities remain underexplored. We incorporate audio and visual modalities as video is a more natural way to represent objects and actions, similar to how humans consume information in the real world. To fully explore the potential and benefits of multimodal learning and continual learning, it is imperative to extend the traditional unimodal continual learning benchmarks to encompass multimodal scenarios. Therefore, we introduce a standardized multimodal benchmark which aims to simulate challenges in realistic real-world continual learning scenarios while maintaining correspondence with existing unimodal continual learning benchmarks and scenarios. This allows for easy comparison and for the progress in unimodal learning to be translated to multimodal learning. The MMCL benchmark is built upon the VGG sound dataset, which is a diverse collection of corresponding audio and visual cues associated with various challenging objects and actions in the real world. To further ensure accessibility to a wider research community, we have selected a more uniform subset from the dataset with a total number of samples similar to widely used datasets like CIFAR 10. We use approximately 50,000 samples, which are distributed uniformly across 100 classes. This approach mitigates the need for extensive computational resources and memory, making the benchmark feasible for a larger set of researchers. Within the MMCL benchmark, we present three distinct continual learning scenarios, each designed to evaluate different aspects of a continual learning agent and encourages the development of robust and efficient multimodal continual learning techniques. Our empirical evaluation reveals several compelling advantages of multimodal learning over unimodal learning. First, multimodal learning significantly mitigates forgetting. By integrating both audio and visual data, the model maintains higher overall accuracy across all previously seen tasks. This indicates that learning with multiple modalities helps the model acquire and retain information more effectively. Second, multimodal learning provides an improved stability plasticity trade off. Stability refers to the model's ability to retain previously learned knowledge, while plasticity refers to its ability to learn new information. Multimodal learning strikes a better balance between these two aspects, allowing the model to adapt to new data while preserving previous knowledge more effectively. Third, multimodal learning reduces task recency bias, leading to a more uniform performance across tasks. These findings underscore the significant benefits of multimodal learning in advancing the capabilities of lifelong learning in deep neural networks. Further building on the advantages of multimodal learning, we explore the design principles that allow for the better utilization of multimodal data in continual learning. To this end, we introduce our semantic aware multimodal approach, which we dub as SAM. SAM leverages the relational structural information between data points within each modality to effectively integrate and align information across the modalities. In the SAM framework, modality specific representations are initially learned independently through visual and audio encoders. This ensures that each modality captures the essential features and nuances of the data. These modality specific representations are then aligned and fused to maintain a consistent relational structure across both the individual modality representations and the combined representation space. By preserving the relational structural information, SAM ensures that the integrated information are coherent and complementary, leading to a more robust and comprehensive understanding of the data. Notably, our proposed approach utilizes a unified architecture that is able to make inferences under a multimodal setting as well as individual modalities, enabling more efficient training and inference while enhancing the applicability of the method in scenarios where one of the modality might be missing. SAM significantly improves model performance in both class incremental learning and domain incremental learning. In sequential VGG sound, SAM effectively mitigates forgetting and learns robust, well-aligned representation that enhances knowledge transfer across tasks, with notable gains in audio performance. In domain VGG sound, SAM demonstrates its ability to learn generalizable features that are more robust to input distribution shifts, maintaining competitive performance even with sharp changes in input distributions at task transitions. We see similar gains in the generalized class incremental learning setting, whereby the model has to additionally deal with class imbalance and learn under repeated occurrences of classes across tasks, showcasing the enhanced robustness of multimodal learning to class imbalance and efficient forward transfer. Finally, we show that SAM allows the model to localize to the source of the data and focus on the most pertinent features in the input image. To summarize the key takeaway messages, our study demonstrated the effectiveness of integrating multiple modalities for continual learning, highlighting reduced forgetting, enhanced adaptability, and key design principles of our semantic aware multimodal learning approach. We hope that our study will encourage further exploration in this promising direction. Our MMCL benchmark and the code for SAM is available at our GitHub, shared here, and for any questions, please feel free to reach me. Thank you.